Welcome to our NPTEL lectures on advanced power electronics and control. Today we shall continue to discuss with the 3-phase converter. Now we were discussing about in previous class when the firing angle alpha more than 60 degree. So, let us see that how the waveform will work for the half control converter for alpha greater than 60 degree, and this is the mode where discontinuous operations start, and we assume that it is feeding highly inductive load. So, we always start from the crossing of A and C from this point. So, it has been delayed by an angle more than pi by 3. So, till this point actually you can see that when actually this crossover takes place at pi by 2, then T3 and till T3 and D3 conducts. After that, since this crossover takes place, B is no longer most negative phase and it will be natural, this D3 will be stop conducting, and thus then free wheel action will take place through this till the time the T1 is not triggered, and this will be the sequence T3 D3. Thereafter will be an interval of the time where free wheel action will take place, followed by T1 D1, then it will continue. So, in every actually crossing in negative half cycle will there will be a phase shift, and the lower diode will be actually naturally will put off, and this actually free wheel diode comes into the picture. Similarly, it will sequence and you will get a voltage like first CB, thereafter AC, thereafter BA and CB. So, instead of the 6 waveform, in this case you are going to get a 4 waveform. Now, 3-phase full wave half control converter, same thing we will continue. So, discussion is let us trigger T1 at an angle pi by 6 plus alpha. So, T1 D1 will conduct and output voltage will appear across his AC. Thereafter, at omega t equal to 7 by 6, AC becomes most negative and actually D1 will turn off and free wheel action will take place. And if DM is not used, T1 will continue to conduct until T2 is triggered, since load is highly inductive. At omega t equal to alpha plus 5 pi by 6, again free wheel action is completed. So, this is the output voltage, this is CB, this is actually AC, thereafter BA and CB, and this is the current through the thyristor T1, and it will be a square wave kind of thing, and thereafter this is a current through the thyristor T2 and D2. Similarly, it is a current through the thyristor T3 and D3, and this is the inverter interval where actually free wheel diode will conduct, and input current you will have this kind of sequence of 120 degree conduction. So, we require to understand now we can see that the VAN, VBN and VCN will have a same sequence, a 120 degree minus phase shift. So, VAC will be VAN minus VCN, that will be under root 6 V sin omega t minus pi by 6. Thus, this output voltage, average voltage we can calculate. So, we will have a 3 such cycles in 120 degree phase shifted. So, it is be alpha plus pi by 6 to 7 pi by 6, 1 by pi, and since there is 3 intervals, so it is multiplied by 3. So, and ultimately it is under root 6 V sin omega t minus pi by 6 d omega t, and similarly output RMS voltage can be calculated by the same method of integrating over the period alpha plus pi by 6 to 7 pi by 6. Similarly, the input power factor will be actually active power output by RMS power input, that is IPF average voltage by RMS voltage. Now, this is the 3 phase full wave half control rectifier with the freewheeling action, where the triggering angle is less than equal to pi by 3 or 60 degree. Now, in this configuration, first, as the instant of this triggering is basically the crossing over of the A and C. So, from this point actually we measure alpha. Till that time actually T3 D3 was conducting. Now, T1 is triggered, and from the negative half the diode D3 is conducting, and it will be actually commutated at this point when the crossover of B and C takes place, and thus from this point onward T1 D1 will conduct. And it will conduct till the commutation takes place, natural commutation takes place of T1 because of the firing of T2, and till this point actually T2 D1 will conduct, and thereafter T2 D2 will conduct. And after that again, when it will again at the 0 crossing of this point, so there will be a phase change, and here T3 D2 will conduct and same sequence will continue. So, here instead of the 4 pulses previously, we will have a voltage will be a continuous and we will get 6 pulses. So, for the time actually alpha pi by 6 2 plus alpha pi by 2, you will get first CB, thereafter you get AB, thereafter you get AN, thereafter you get AN minus CN, that equal to VC, thereafter BA, in between you get CA, again you get CB, you get AB, and such a way it will continue. And current through the thyristors, you will find that actually it will be delayed by some angle alpha from this actually pi by 6. So, it will continue to 5 pi by 6 plus alpha, and thereafter again it will continue after pi by 2. So, similarly D2 will conduct for the time 7 pi by 6 to 11 pi by 6 and so on, and effectively you will see that actually the in phase current IA will be actually conduct from pi by 6 plus alpha to 5 pi 6 plus alpha. Similarly, again it will conduct from 7 pi by 6 plus alpha to 11 pi by 6 plus alpha and so on. Now, we require to again calculate what we have done in case of the alpha more than 60 degree, we require to done also alpha equal to and less than 60 degree. So, value of the RMS voltage, value of the average voltage is given by same thing, it is alpha plus pi by 6 pi by 2 VAB plus there will be a limit change because it was 0 otherwise in the previous condition. So, pi by 2 alpha plus 5 pi by 6 VAC d omega t. So, from there the value will come out to be 3 root 3 Vm by 2 pi 1 plus cos alpha for this alpha less than 60 degree. So, what will be the value for this condition? Similarly, for RMS value we can also calculate. So, this value comes out to be that root 3 Vm 3 by 4 pi 2 pi by 3 plus root 3 cos alpha square whole under root of 2. So, this will be the average and RMS value for alpha less than equal to 60 degree. So, expressions of the voltages of the half control converter will be changing depending on the triggering angle. Now, let us introduce, because we have seen that that we shall discuss little later about the power quality issues. Since we have a more number of pulses within a cycle is more, it is easier to rectify, and moreover, so distortion of the current in input the AC side will be less. Considering that, can you use a multiple diode based rectifier, that is the simplest because you do not require in a triggering circuit, and thus we can reduce the THD and other parameters which is actually conflicting while AC to DC conversion. So, for this reason we have to keep in mind to reduce the line THD, to improve the input power factor and avoid the semiconductor devices in series to have a higher rating. So, for these things let us come back again our natural 6 pulse converter we have discussed in initially. So, and we assume that it is feeding a resistive load and actually VAB equal to VA minus VB, it is actually root 2 VLL sin omega t plus pi by 6. And so, 6 pulse you can find it out what is actually the waveform. Waveform will be like this. So, this is for the area A1, same kind of area will be available for other. So, you can get due to that what happened, the current will have this kind of actually the profile. So, for here D1 D6 conduct and here D1 D2 conduct. So, actually the output voltage due to this diode can be actually you will have a 3 such area. So, area A1 by pi by 3. So, 1 by pi by 3 you have to integrate actually since this area is basically sin AB, you can see here basically sin AB voltage. So, pi by 6 by pi by 2 root 2 VL sin omega t plus pi by 6 d omega t. So, it is 3 root 2 by pi VLL, that is basically that DC voltage comes out, average DC voltage comes out to be 1.3 type of line to line voltage. So, that is something you require to keep in mind while you use for a 6 pulse converter, 3 phase 6 pulse converter. And what happened these things become little drastically changes and when you have a RC load. The current will conduct, assume that this value is VD, current will conduct once this actually the most positive phase is more than this actually the VDC or VD. So, for this reason for this small interval where actually phase AB is more than this the output of VD, so current will conduct. Similarly, it will conduct for a very small interval of time. So, accordingly you will have this is the input current and which is very much contaminated with the harmonics. And this is a critical case when basically we want almost a huge DC capacitor to make it ripple free, and due to that you pay the penalty in the input side having very degraded value of the displacement power factor, THD and all those issues. And the current through the diode ID will have this kind of pulses. So, it is not a constant current. So, let us take a 6 pulse converter with a discontinuous current mode. What happened here till this value VAB is actually more than this rectified voltage, till that time current will not flow. So, current will start picking up at a point let us say theta 1. So, when actually VAB crosses and VAC will have a phase lag of pi by 6. So, once actually at this point once again it will 0 crossing takes place. So, then what happen, capacitors current continue to flow, due to that reasons actually you will have the current will come back like this. Since till this value voltage line voltage AC will again cross this actually the VDC, this no current will flow into the system, and thus you will have this kind of current, and the theta 1 can be calculated, that is actually sin inverse of VD by this, and theta 2 definitely is going to be pi minus theta 1. So, we can have a continuous current operation if we increase the load, and thus value of the VDD will come down, and what we will find that this is basically the IA, and this is basically the IB, and this is basically the IC. So, when we increase the load current, then actually current becomes continuous. So, we require to increase the load. So, ultimately that IA become this, and IB become this, and IC become this when it is positive half cycle, and the current through the diode will be a continuous one. And then what happen in some interval of the time when on state of the diode, for example, when IA is conducting, that when current is flowing like this. So, automatically return path will be by the sum diode. So, what happen, IA will be conducting once actually current is increasing. So, D1 and D2 will conduct, then after that this interval region 3, what happened. So, you can see that in this region IA falls and IB picks up. So, for this reason you will find that since IA falls, D1 still conducting as well as D3 comes into the picture for the forward part of the circuit. So, D1, D2, D3 will conduct. Gradually after gradually an IA will become 0 and D1 will be off, then D2, D3 will conduct. So, there will be a overlapping zone where IA and IB both are conducting in this mode of operation. So, with the increasing load current, the rectifier will enter into the continuous current operation, and during commutation interval there are actually 3 diodes put into the operation. Now, there is an example we can cite. The rating is a quite high value rectifier. So, it is a USA system, for this it is a 60 Hz. So, we have 4160 volt 2 MVA rectifier and base current as high as 277 ampere, and base inductance of this value. Line inductance will have let us say 2.29, that is 0.1 per unit, and line current is assumed to be actually if it is actually half of the rated current of 277 will be this one. So, we can find that what is the harmonic content in it. So, this is the basically the blue one is essentially the load input current is feeding to the RC diode based rectifier feeding RC circuit, and this black current is the fundamental one. So, we can see that in case of the, and this is second case where per unit value is 0.2, and this is second case where per unit value is 1. So, where current rating is 1, and thus these things become continuous, and this is basically discontinuous almost. So, you can see one thing here, if load current is low, so it is discontinuous in nature mostly, and the harmonic content will drastically increase at low load current. So, you can see that fifth harmonic is 63%, seventh harmonic is 38% and so on, and thus overall THD coming out to be the 75% in case of the diode with 6 pulse diode based rectifier feeding a RC load. But where it will become a per unit, it is actually carrying the rated current, but heating effect will be there, other issues will be there, but as far as the THD is concerned, this will be reduced because of the continuous conduction mode. So, THD will come down to be the actually 32%, and basically this current is 30%, there are 8%, and other values you can check, it is almost half. Now, what happened? This is a case of showing how THD decreases with the load and with different values of the source inductance. There is an effect of the source inductance. First case A, you can see if source inductance is low, you will find that THD will be actually higher, and once you actually increase the load current, of course, the THD will come down. Same thing for different values of the source inductance. And what happened the power factor? You will find that actually increasing the load, power factor will improve, because displacement power factor gets actually reduced. You can of course assume that, but apart from that, due to the source inductance, you will find that power factor is least in case of the A. It gradually reach out its maximum value when it is actually reaches its peak value, and B is actually the middle point in the row. So, actually it will be in the half point, and after some time, let us say 0.5 unity power factor, 0.5 of loading, you will find that source inductance effects almost mitigated as far as power factor is concerned. Power quality mostly consists of THD and the power factor. So, you can find that source inductance, increase the source inductance basically decreases the THD, but here after 50% of the load current, so source inductance does not have a much effect on the power factor. Now, let us analyze with the 12 bus converter, but to have the 12 bus converter, we require to have some configurational changes, and we require to have a transformer in the system, and whose actually you should have a different kind of transformer. You can, and here generally this part is delta, and you have also the delta star transformer, and it has a different kind of vector group to operate. So, in this case what happened? You have a phase shift between this line current and this line current by 30 degree, and since IA is basically primary current is IA, if it is a 1:1 transformer, we will have split it between the star and the delta part. The phase shift between the transformer is basically 30 degree, and secondary line to line voltage, it is VAB equal to VB delta equal to VAB by 2, and let us assume that actually N1 by N2 equal to 2 and N1 by N3 equal to 2 by root 3. So, this is the trans ratio. So, you require a special configuration of a transformer to have 12 bus converter or 12 bus rectifier into the system. So, what happened here, you will find that why it is 12 pulse, because there will be a 2 current, basically this is the current for delta and this is the current for star, and thus actually it makes out to be the star and delta, and ultimately you will have total 12 pulse into the system. And you can find that VAN by A1, that is a fundamental, that a fifth, that a 7, and overall THD has drastically reduced to 24% from the 35% in case of the RC feeding circuit. We have taken a same kind of load, but we are actually having a 12 bus converter. So, and the current profile you can see, it is a close to the sinusoidal, and thus harmonic control is left, and what you can find out that there is no harmonic content in the primary, because this is basically the IN 1 by A1, it contains fifth and 7, it contains fifth and 7, but in case of the input current, it does not have fifth and 7 harmonics. So, 6 n plus harmonic is totally eliminated, you just have 11 and 13 harmonic and so on. Similarly, 6, 17 and 19 harmonics is eliminated. So, thus THD in case of this delta part was 21% and the star part was 24%, but input side it just gets reflected only 8%. So, it is drastically reduced from the previous value. So, this is a great achievement from the power quality point of view, but you require to incorporate extra cost on the transformer. So, let us have a performance analysis, and you can have A, that is source inductance is 0, and you can see that actually increasing the load with load current, THD will be as high as actually near close to the 20%, but it will come down close to actually 8%. And thereafter, if it is actually has a source inductance, then actually it may comes further. So, this is the comparison between the 6 pulse and the 12 pulse converter. 12 pulse converter gives you a quite low THD. Same what happened, let us see to the power factor. Power factor, you know, actually in this case will have little bit of detrimental effect. So, you will start from the high power factor, and this will not change much if there is no source inductance, but with the effect of the source inductance you will find that power factor will decrease, because you have put an extra inductance into the system. Thank you for your attention. We shall continue to the part of the different kind of pulse converter in our next class.